Let's try this problem that I gave you at the end of last class, at the end of the last video. And I gave you this matrix, -5, -9, 3, 7, and asked you to diagonalize it. So let's start by doing this. Hopefully this went well, but let's see what we can do. So the first thing we need to do is find eigenvalues. And to do that, we do that determinant A minus lambda I. So we take that determinant, -5 minus lambda, -9, 3, and 7 minus lambda. And we sort this out, and we try to find out when this determinant is equal to 0. Okay, and this ends up being an algebra problem. And so this is -5 minus lambda times 7 minus lambda minus plus 27. Okay, so it looks to me like we get -35 minus 7 lambda plus 5 lambda plus lambda squared plus 27 equals 0. Let's come over here. I always like to try to get it organized. I like to put my positive lambdas first. Minus 2 lambda minus, and then it looks like I've got 8 equals 0. And then I bet this factors. If it doesn't factor, you can just use the quadratic equation. But let's see, it looks like we get a 4 and a 2, right? So lambda minus 4 and lambda plus 2. That looks like it works, doesn't it? So we get -8 right here, -4 lambda and 2 lambda. Okay, so there we go. So there's our eigenvalues, -4 and 2. And so for each eigenvalue, we'll go find an eigenvector. So let's find the lambda equals 4 eigenvector and see how that works out. We're going to take that matrix and I'm just going to put 4 in right here. And that's going to give me -5 minus 4 will give me a -9, and that one's a -9, and this will be 3. And the 7 minus 4 is also 3. And this is 0, 0. And if you're playing along, you can see how this row reduces. We've done a bunch of these. What if I just cut straight to the answer and notice these become zeros, divide by -9, I get 1, 1, 0, 0, 0, 0 for my row reduced solution here. Okay, this is nice because this means x plus y equals 0. And so that means my solution is x plus y. That means my solution is that x equals -y. So my solution is either 1, -1 or -1, 1 because x equals -y. And so I guess I could write that out down here for you. So we get xy equals, x is -y, so -1, 1, y. So that looks like a pretty reasonable eigenvalue. So here's my eigenvalue 4, my eigenvalue 4, and my eigenvector of 1, 1, -1. Okay, let's try the next one. And so my next one here, let's just pick this piece of paper up and replace it. And so my next one was -2 was my next eigenvalue. So I've got lambda equal -2. And now I'm just going to go in and just plug, again, I'll just plug -2 right in here. And that'll kind of tell me what I'm going to be doing. So -5 minus a -2 is -3. And then +3. And then -9 minus, that's a -9 by itself. And then lambda 7 minus a -2. Hold on a second. Did I mess up? 4 obviously worked. And -3. And hold on a second. Let's see. I feel like I messed up somewhere. I feel like this isn't working. Okay. because I feel like this one should end up being positive 9. And it's, oh, and it is 9. Ah, sorry. I was, oh, okay, well, okay, folks, this is where, again, if I wanted to be professional, I would delete all this and start over again. But you know what? I don't have the time or willpower to do that. So you all can tolerate my, my flailing around. Okay, but at any rate, we've got -3, 3, -9, and 9. And then we can see that this all wipes out. And I'm going to divide everything by 3, and I'll get 1, 3, 0, and then our other row becomes zeros. So that's what I get. And you can see that I have x plus 3y equals 0, and so x is -3y. So that means my matrix xy is -3, 1 times y. So I have my second eigenvalue of -2, and then I've got -3, 1. I could do 1, -3. Let's stick with that. So that seems pretty reasonable. Okay, now, so I have my two eigenvalues, and I have my 2 eigenvectors. So now I'm ready to start setting up my diagonalization. So how do I diagonalize things? Well, I need those 2 matrices. I need the P, and then the D and the P inverse. And so for my P matrix, I just put my 2 eigenvectors in there, and I can put them in any order. So I'll put that first one first, -1, 1, and then put that one second, -3, 1. And so there's my P matrix. And my D matrix is just the matrix that has my eigenvalues on the diagonal. My first eigenvalue was 4, and my second value is a -2. Again, I can switch that order, but I also have to switch that order, right? And I could have used a +3 and -1, but then I would get a different P inverse down here when I do this one. So my P inverse is the inverse of this, and so I do the inverse by switching those spots, get 1, -1, and then switching those to positive and negative, but then I have to divide by the determinant. The determinant of this is -1 minus a -3, so it looks like 1/2 is what I've got. Okay, so that's my P inverse. I guess I could write it out if I wanted. I could write it out as a 1/2, a -1/2, a 3/2, and a -1/2. So I can either write it in the form where they're all fractions, or I can put that fraction in front. But at any rate, I can now see right now what the diagonalization is. So my diagonalization is simply -1, -3, 1, 1 times 4, 0, 0, -2 times, and then 1/2, -1/2, -1/2, and 3/2. And so that diagonalizes it. And again, if I wanted to raise this vector to a really large power, what would that do? We would just raise this to a really large power, and those two would stay the same. It's not usually bad to check your answer. Let's go ahead and check this answer just to make sure it works. Especially since I almost messed up in the middle. I'm going to start by multiplying those two. You can, of course, multiply them in any order as long as you don't rearrange the order, because you can't switch them. Okay, but I decided to do these two first because that'll get rid of my fractions. So row 1 times column 1 is just 2. Row 1 times column 2 is 6. -1, no, +1, sorry, and +1. See, I got that right. So 4 times 3/2 is 6. -2 times 1/2 is 1, and 1. Okay, and now we'll multiply those together. -2 minus 3 is -5. -6 minus 3 is -9. 2 plus 1 is 3. 6 plus 1 is 7. And look at that. We got the original matrix that we had. So here's our diagonalization. That's how you do it. So to diagonalize a matrix, you simply find the eigenvalues, find the eigenvectors, and then set up your diagonalization just like that. Okay, as we end here, I want to talk a little bit about this theorem and why this theorem should be true. So we had this theorem that we started with, which was what we called the diagonalization theorem. And the diagonalization theorem just said that if you have a matrix, you can write it as these eigenvalues. Let's think about why. First, let's think about why it should be true from an algebra standpoint. So first, we have to think about what is an eigenvector. Well, an eigenvector is a vector that when you multiply the matrix by that vector, you just get lambda times that vector back. So that means that you had that vector, you multiplied it by your matrix, and you got the same vector, but at a different length. And so either that length got longer or shorter, but the vector itself didn't change direction. It continues to point in the same direction. Okay, so that's what an eigenvector is. So what if I take this formula, A equals PD P inverse, what if I just multiply both sides by P? And then you'll notice that this formula becomes AP equals PD, because those two become the identity. Well, let's ask ourselves, what is A times P? Well, that is A, and P is our matrix that's just made up of our eigenvectors. Well, all we do is we do A times the first vector and A times the second vector. So that just means that we get lambda times that first vector and lambda times that second vector, because all A does is it just stretches those two vectors by whatever the eigenvalue is. Okay, but at any rate, if I look at PD, so that's this part. If I look at the second part, which is the P times D part, well, that's just my two eigenvectors times lambda 1, lambda 2 with zeros in here. And then I just do, row times column. Well, the column is just lambda 1, so we end up just getting with lambda 1 V1 and lambda 2 V2. So you end up getting the exact same thing in this case. So okay, so here you go. We ended up getting the exact same thing looking at both sides of our equation. But there's a geometric way to think about this, and I think the geometric way is super valuable. So let me pull out my picture that I drew before we started and hope that it makes a little bit of sense. Well, if these two vectors, my red one and my green one, are my eigenvectors, then normally what would happen is those eigenvectors would just get stretched. So perhaps this first eigenvector would just turn into some longer version of that eigenvector. And that's what it means to be an eigenvector. It just gets stretched. And this second eigenvector would get turned into some, in this case I have a shorter version, but some stretched version of that eigenvector. They could be flipped or something like that. Well, we could think about it. Instead of doing this directly, you could think of it as going in some circuitous route, where instead of going from here, we take these eigenvectors and convert them to the elementary bases. Well, we know how to convert elementary bases to an eigenvector. The way you do that is we take these elementary bases and turn them into our eigenvector, where this is E1 and this is E2. And so our elementary bases, we just multiply by the matrix where E1 is V1 and E2 is V2. So we just multiply by this P matrix, which is that matrix that has V1 here and V2 here. So if you remember, that's how you take the standard base, the elementary bases, and turn them into any bases. So if we want to turn the eigenvectors, we just multiply by that matrix. Well, okay. So if we were going that way, then to go backwards, we just take the inverse of that matrix. And so P inverse would turn these eigenvectors into elementary bases. Okay. Now, what does a diagonalization do? A diagonalized matrix, which is that matrix lambda 1, lambda 2 with zeros on it, a diagonalized matrix just stretches. So notice this is multiplied by E1, and so E1 just gets stretched by that lambda value. So this becomes lambda E1, and this one just becomes lambda 2 E2. So all that happens are this diagonalization matrix is just a stretching matrix. And then what happens is now we do P again, and we convert those standard bases back to our eigenvalues, but now they're stretched versions of the eigenvalues because we have stretched versions of our elementary bases. So what you can think of is you can think of the diagonalization process as a process of taking your eigenvectors, turning them into the elementary bases, stretching them, and then turning them back. And if you think about that, then that gives you a nice way of kind of thinking about what it is that these eigenvalues do. The eigenvalues are the stretching process that happens in this conversion. And if you think about it, what that means is that in order to get to A, getting to A is the same as multiplying by P inverse, but notice we always write the last one first, P inverse times D times P, because if I had any vector here, I could just say A times that X times that vector, or I could do P inverse times that vector, D times that, and P times that. And so you can see from this picture that A equals PD, P inverse makes a lot of sense. Okay, well, this picture is kind of the crux of the next chapter in the next section in the book, which is, let me grab it real quick. This picture is at the heart of section 5.4, and I really like 5.4. As you can imagine, I can talk about it for a long, long time. But I think for the sake of this online version of linear algebra, we're going to skip 5.4, and we're going to jump right ahead to 5.5, which asks, well, what happens if we have a complex eigenvector? And it turns out we have a similar type of picture, except now, instead of a stretching happening here, what we get is we get a rotation happening here. And so that's going to be the difference between a complex eigenvalues and these normal eigenvalues. But we'll talk about that next time, and we'll go into detail on how to do that. So.